Section 5.2, Exploring Quotients of Polynomial Functions. By the end of this lesson, you should be able to define a rational function, explain the difference between a continuous or discontinuous rational function, and state the types of discontinuities based on the equation of a rational function. So what I would like to stress is today is effectively just an introduction to rational functions and looking at the various properties of rational functions. So we're just going to take a look at some graphs and discuss their properties. So recall that a rational function is any function that can be expressed as f of x is equal to p of x over q of x, where p at x and q at x are polynomial functions, and remember that the denominator cannot be equal to 0 because that would result in an undefined quantity. Essentially, a rational function is a function where there is a numerator and a denominator that are not 1. An example of a rational function would be f at x is equal to x squared plus 1 over x plus 3. That's a rational function because we have a polynomial on the top and a polynomial on the bottom. Right? We don't have a numerator and denominator that are both equal to 1, and the denominator will have a restriction, so that's not equal to 0. The function f at x is equal to x squared plus 1 over the square root of x plus 3 is not rational because this denominator right here is not a polynomial function. So it's got to be a polynomial on the top and a polynomial on the bottom. That is a rational function. Let's just quickly take a look about, to talk about discontinuities. Rational functions can be both continuous or discontinuous. So they can be continuous in the sense that there's no jumps or holes or asymptotes, or they can have holes, jumps, or asymptotes. So rational function f at x is equal to p at x over q at x is continuous only if the denominator can never equal 0. So for example, I've graphed this function right here, x plus 2 over x squared plus 5, and as we see, that results in a continuous rational function because there is no value in the denominator, rather no real value in the denominator that would cause the denominator to be equal to 0. So a rational function will, however, be discontinuous if there are real values of x that will cause the denominator to become 0. And if that's the case, we're going to have either a vertical asymptote or a hole. The other types of asymptotes that we can have are horizontal or oblique asymptotes, so asymptotes at an angle, and those can also exist on graphs of rational functions. So the next section asks you to use Desmos to graph the following rational functions, but I've already done that for you, and I'd like to quickly take a look at the ones that we've done. Let's just take a look at number 1. So I've given you two polynomial functions here. Okay, I've given you p at x and I've given you q at x, right? What I've done right here is I've taken q at x and I've simplified it. I factored out the negative, so q at x is equal to negative bracket x squared minus 1. So take a minute, pause, copy what you see on the screen, and copy the functions. Okay, I'll give you a second. Okay, so hopefully you paused the video and now you're back. The first function that we've done here is x plus 1 over negative x squared minus 1. As you can see, we have two asymptotes. Let's start with the vertical asymptote because the vertical asymptote is the easiest to see. Is there a value for x that would cause the denominator to be equal to 0? Yes, 1, because 1 squared minus 1 would be equal to 0, so we have to have a vertical asymptote there. We also have a horizontal asymptote at y is equal to 0, and that's because if we look at the end behavior of this function, we would see that as x goes to negative infinity and as x goes to positive infinity, this rational function will go towards 0. Okay, so as we move towards negative infinity and as we move towards positive infinity, the value of y's will approach 0. Now, say we flip this fraction and then we do q at x over p at x. Well, we end up with this line, except this line has a hole at negative 1, 2. As you can see, I've included it right there. It's just a line, but there's a hole on that line. And remember, it says right up here, you can have basically a discontinuous function, so it can have a hole in it. The reason for that is as follows. If we flip this, we would have negative x squared minus 1 over x plus 1. Well, you should see immediately that x squared minus 1 is a difference of squares. So this can be factored over here, x minus 1 and x plus 1. What will then happen is that the common factor, that is x plus 1, would cancel. So this would cancel and that would cancel. And we would be left with negative bracket x minus 1, which is the equation of a line, right? And if I just expand in, y is equal to negative x plus 1. So that's the equation of a line. But we have to include that that line cannot have a value of x at negative 1. Because when we look at our original function, where that came from, I had x plus 1 in the denominator. So because x plus 1 is in the denominator, x can never equal to negative 1, even if it gets factored out, even if we cancel it. Because the original function had x plus 1 in the denominator, x can never equal to negative 1, and as a result, we have a hole in that graph. Looking at the next set of functions, our rational function here, p at x, was equal to negative x plus 3 over x squared plus 1. Immediately you will notice that there are no asymptotes here. And there are no asymptotes, right? This is going to be a continuous function because if we look at the denominator, there is no value of x that would cause the denominator to have a value of 0. Again, there is no real value of x that would cause this denominator to go to 0. As a result, we have no vertical asymptotes. All right, if we flipped that, right, we would end up with this graph right here. And please note the scale is different than the scale that you see on your page. So you can just sketch this and ignore the scale on your graph. What you should see right here is that we end up with x squared plus 1 on the top over negative x plus 3, and we have two asymptotes. We have a vertical asymptote at x is equal to 3. That's because if x is equal to 3, then my denominator would become 0 and this would become undefined. So I have to have a vertical asymptote at x is equal to 3. I have a slant asymptote or an oblique asymptote because the numerator is 1 degree higher than the denominator. Let me repeat. We have a slant asymptote because the numerator is 1 degree higher than the denominator. And again, we're not going to go into detail about that now. We're going to cover that later. But that's all you need to know for now, is that if the numerator is 1 degree higher than the denominator, you will have an oblique asymptote. The final graph that we have is x over x minus 2. So the first thing again that I'm going to do is I'm going to look at my denominator and I'm going to see that I have a value for x that would cause this to be undefined. That's 2. So I have to draw a vertical asymptote at x is equal to 2. I also have a horizontal asymptote at x is equal to 1. And again, I can get that horizontal asymptote by looking at the end behavior of my function. As x goes to negative infinity, well, this function will approach 1. And as x goes to positive infinity, it will also approach 1. So we have to include a horizontal asymptote at x is equal to 1. Same thing over here. I'm going to flip it. I've got x minus 2 over x. I know my value for x that causes a restriction is x cannot be equal to 0, so I have a vertical asymptote there at x is equal to 0. I've slightly shifted it off the y-axis just so that you can see the y-axis, but it's right there. And then I have a horizontal asymptote at y is equal to 1, right? And at y is equal to 1, I have a horizontal asymptote. Again, that is by looking at the end behavior of this function. How does this function behave as x goes to negative infinity? And how does this function behave as x goes to positive infinity? So on the next page, it asks you to take a look at all these graphs, right? And start answering these questions. For each of the 6 rational functions you graphed above, answer the following. Where are the zeros? Are there any asymptotes? What are the domain and range? Is it a continuous function? Are there any values of the equation that are undefined? And what is the significance on the graph? Then also, what are the end behaviors of this function? So what I'm going to do is I'm just going to pause the video right now, and I'm going to ask that you go back and refill, answer all those questions for yourself, and then when we come back, we'll check the answers. Okay, so here are the answers that I came up with for 1A and B. You can pause the video at this point and check your work. These are the answers that I came up with for 2A and B. And again, pause the video and check your work. Please note that for 2A, we don't need to know how to achieve the range for that, right? That's not something that we're going to cover this year. That's a bit more challenging. So we're not going to look at how to find the range for a graph like 2A. Okay. We will, however, look at the range for 2B. But what I'm going to say for 2B is you don't need to know how to get this equation just yet. Maybe you were able to get it from the graph, but y cannot equal these values. And I'll show you later how that's done. Okay, and there's your answers for 3A and B. What I would kindly ask is, since I did this rather hastily in order to make this video, if you notice any errors, please let me know. Again, I did this relatively quickly, and I think you can probably empathize that when math is done quickly, there's lots of room for error. So please let me know if you see anything. Discontinuity. The rational function f at x is equal to p at x over q at x has a hole at x is equal to a if p at a and q at a are equal to 0. That is, if the numerator and denominator are both equal to 0. So that happens if there is a common factor. So we end up, if we start with a rational function like this, as you can see here, I have a polynomial in the top and a polynomial in the bottom. But then when I factor, I get x minus 2 times x plus 4 over x minus 2. As I've written here, there is a common factor, which is x minus 2. So at the value of 2, when x is equal to 2, the numerator will become 0, because 2 minus 2 is 0, then 0 times 6, because 2 plus 4 is 6, that's going to be equal to 0. The denominator is also equal to 0, right, because 2 minus 2 is equal to 0. So we end up with a hole at x is equal to 2. Because these common factors will cancel, we end up with the equation of a line, but I still have to state the restriction that x cannot equal to 2. So there is a hole at x is equal to 2. We can also have discontinuities that are vertical asymptotes, and these are the ones that you will probably see the most, right? Or not see the most, but rather maybe are most familiar with, right? And we have a vertical asymptote when we look at the denominator. We note that x cannot be equal to negative 2 because that would cause the denominator to equal to 0, so therefore I have my vertical asymptote at x is equal to negative 2. Now, why do I have this horizontal asymptote at y is equal to 1? Well, again, we have to look at the end behavior of this function, and that's what it says. For the horizontal asymptote, look at the end behavior. As x goes to negative infinity, this function goes to 1. And that's because as x gets increasingly more negative, we have like a very large negative number, right? So say we have like negative 1,000 in the numerator. Well, negative 1,000 plus 1 over negative 1,000 plus 2. Well, that's just approximately equal to negative 1,000 over negative 1,000, which is just 1. So we ignore the plus 1 in the numerator and the plus 2 in the denominator here when x approaches negative infinity because they are insignificant in comparison to negative infinity. So this gets so negative and large that the plus 1 and the plus 2 don't matter, and then we just end up with negative over negative, which is just 1. Same thing with positive infinity. If we go really, really high, let's say we had x is equal to 1,000,000. Well, 1,000,000 plus 1 divided by 1,000,000 plus 2, that's pretty much going to be equal to 1. It's going to be pretty close to 1. So we have a horizontal asymptote at y is equal to 1, because as x goes to negative infinity and as x goes to positive infinity, this graph goes to 1. Okay, discontinuity, horizontal asymptote. So there's a couple of things here. The rational function has a horizontal asymptote only when the degree is less than or equal to the degree of the denominator. So when the numerator and the denominator have the same degree, we have a horizontal asymptote. If the numerator has a lower degree, then we have a horizontal asymptote. Okay? So this is the important part right here. Horizontal asymptote, okay, only when the degree of p at x is less than or equal to the degree of q at x. So another way of writing that is if the numerator degree is less than or equal to the degree of the denominator. If the degrees are equal, then the location of the asymptote is given by dividing the leading coefficients. So these are my leading coefficients, 3 and 2. So here, the degree of the numerator and the degree of the denominator are both 1. So they have equal degrees. If they have equal degrees, that means that we're going to have a horizontal asymptote, and we have a horizontal asymptote at y is equal to 3 over 2. Okay. Otherwise, the asymptote is at y is equal to 0. This is because as x gets very big or very small, the denominator gets much bigger. So in this case right here, our denominator is greater, the degree of the denominator is greater than the degree of the numerator. Well, that means that as x gets really, really big, this denominator grows larger, much larger, because it's squared than the numerator. So something with a very, very big denominator is pretty close to 0. Okay? So here, the asymptote is at y is equal to 0 since the fraction approaches 0 as x gets very large or very negative. So right here, as you can see, I've got my vertical asymptote for this right here. That's the easy one, right? I can see that x can't be equal to 2, so I have to have a vertical asymptote there. But then I look. The degree of the numerator is the same as the degree of the denominator. So I follow this rule. If the degrees are equal, the location of the asymptote is given by dividing the leading coefficients. Well, the leading coefficient is 3 divided by 2, so I have a horizontal asymptote at equal to 3 over 2. And so I'm going to include that right now. Okay, so I've included my horizontal asymptote here at y is equal to 3 over 2. I have my vertical asymptote right here. X is equal to 2, and so I'm able to graph this function. The last discontinuity we're going to look at is an oblique asymptote or a slant asymptote. And this is what I would like you to highlight right here. The rational function has an oblique asymptote only when the degree of the numerator is exactly 1 greater than the degree of the denominator. So let's write that in. When the degree of numerator is exactly 1, right? So is exactly 1 greater than the degree of the denominator. Okay, but before we go and look at this example, we saw an oblique asymptote earlier in my examples. Let's just quickly take a look at it. Okay, here we go. We had our oblique asymptote, and as I stressed in the video, the numerator was degree 2, the denominator was degree 1, so the numerator was degree 1 more than the denominator. Okay, again, we see here the numerator is 1 degree higher than the denominator's degree, so we have a slant asymptote. Okay, we also have a vertical asymptote at x is equal to -2. That one's easy to find. The slant asymptote, however, is achieved by dividing the numerator by the denominator using long division. So the slant, the equation of the slant asymptote is equal to x minus 2. And there we have our slant asymptote. There is not a lot of homework, as you can see here, just questions numbered 1 to 3 on page 260. Thank you for watching.